We continue our discussion of the binomial option pricing model to explain option values. And so far we have a one period, two-state model. And we want to generalize this. At least we want to have a look at the multi-period model, especially two periods. Okay, so what we can do is we can start with pretty much similar assumptions. Let's assume that the stock price starts at $100 again. And also let's assume that the strike price is $110, except that now we will have two periods and each one being 6 months. So therefore we are breaking the year into two 6-month periods. So as a result, I will be calculating C1.5, so for 6 months from now, and then finally S1. And in order to calculate these, I need the up factor and the down factor. Let's assume that the up factor is 1.10 and the down factor is 0.95. And lastly, let's also assume that the interest rate is 5% semi-annually. And again, let me remind you that this is a two-period model. So this is a two-period model. So this will be a nice extension if we can of the single period model. If we can make sense of the two-period model, then the model can obviously be easily using some computer programs, for instance, which can easily do the computations into generalized into maybe quarterly, like to a 4-period, and then eventually monthly 12-period, and so on. So eventually you can have 365 days in a year. So you can further divide the 1 year into smaller and smaller, finer and finer pieces. But if you go ahead and start with the stock price tree, you start at $100 and you have two nodes, up or down. And because the up factor is 1.10 and the down is 0.95, stock price at the end of the first period will go up to 110 or will go down to 95. And now we can further do the following. We can further at each node, again, we can either go up or down, up or down. And if you further go up in the chain, so we will further multiply 110 by 1.1, and that will obviously give us 121. 95 times 1.1 will give us 104.5. And notice that that's the same as 110 times 0.95. So therefore, there are two different ways you can come to that node. And so finally, the last node will be where I follow down, down. And that's 0.95 times 0.95 times 100. So that will come out as 90.25. All right, so this is our stock price tree, but by the same token I can create a call option tree as well. So again, we will have up and down. I'll call the first as CU and CD, what happens at the end of the first period, and then just the same way we proceeded with the stock price, I'll call this one as CUU, this one as CUD, or you can as well call it CDU as well, that's the same thing, and finally CDD here. And we will be calculating this. Obviously, the last node is quite easy because we already know the prices. So the call option will expire in the money here. So it will be 121 minus the strike price of 110. That would be $11. In this node, 104.5 is less than the strike price, so that would expire worthless, and the same thing here, worthless. All right, so based on these figures, I'll go ahead and start calculating CU first, then we will look at CD, and then finally, once we have CU, CD, we can calculate C. So basically what I'm doing is I'm dividing this problem into sub-problems where I first focus on that single one-period model here, where the starting node is CU and the ending nodes are CUU, CUD basically. All right, so For this one, we will go ahead and calculate the replicating portfolio. Portfolio. And for that, I need the delta hedge, obviously. So the delta here would be equal to 11 minus 0 divided by 121 minus 121 minus 104.5. And that will give me a ratio of 2/3. Which is pretty neat. Now that tells me that the replicating portfolio in reality is the following. It is to buy 2 shares of stock at $110, obviously, and actually this one is buy, or and I should say write a call option. Well, actually write 3 call options. 3 call options, and well, each one will be written at the price CU, obviously. Do you guys agree that this is the 2-to-3 ratio, 2-to-3 ratio here? So based on that, going back to the blue color, we have the following cost. Let's first calculate the cost of building such a portfolio at time 0, or at time 1 here. Or 1.5, if you will. The 2 shares at 110 that were acquired at 110 will cost us 220. And because we are selling 3 call options minus 3 times CU. That's the original cost. Now, what happens at the nodes? So for this replicating portfolio, we will either have an up or a down movement. In the up movement, the stock price goes up to 2 times. Well, our outcome at least is 2 times $121. Let's write that down. 2 times 121 minus 3 times. I say minus because we wrote 3 call options, and the call options expire in the money at that node, so minus 3 times 11 basically, and this has a cost of 242 minus 33, which is $209. At the down node, that would be 2 times 104.5, so 2 times 104.5. Let's put brackets, and then the call options expire worthless, so that cancels. 2 times 104.5 is 209. But then that's perfect. So this is exactly what we wanted to achieve. We achieved a riskless result. So we in a sense replicated the bond portfolio. So therefore, by the no arbitrage principle, because these two because we have this riskless result, this portfolio that we have just created, the cost should be equal to the cost of this of a bond security, which pays $209 at the end of 6 months. So for that, 209, this happens because of the no arbitrage principle, or you might say because of the law of one price. So 209 minus 1.05 better be equal to this figure here. So 220 minus 3 CU. And you can solve it easily for CU, and that would be equal to 6.984. And so we have a number for this node. Now we need to do the same analysis here, but for this one I don't have to do the delta. Actually, if I do, I realize that the numerator will be 0 minus 0, which is 0, so the delta will come out as a 0. So as a result, or even better, because we are not expecting any value following that path, obviously CD, the node here, should be $0 as well, right? So because CUD is equal to CDD, which is equal to 0, this would imply that CD itself, oops, that's a C, CD itself is $0 as well. All right, so that's actually I can just drop the dollar sign. Okay, there you go. Now it's time for us to solve this one period model, this one period tree. And so for that, let me just remind you of the stock price one. So we had the 100 here, and then we had 110 and 95. That's for the stock. And for the call option that we want to assess value, we have the following nodes. The up node is 6.984 and the down node is 0. But then we can go ahead and create yet a new replicating portfolio, and it should be easy to calculate it again by delta hedging. So the delta is the difference in the call payoff, so 6.984 minus 0 divided by the difference in the stock prices. I mean, in the stock price at time 1 and a half, at 6 months later, for the two different states given, and so point minus 95, and that's simply equal to 0.4656. So that's the delta. We can directly create our replicating portfolio. As usual, it will be pretty much the same idea. So our replicating portfolio, we will buy, well, we can buy this amount. I know it's silly, but shares of stocks, and we would write one call option, and that's it. And so based on this, let's first calculate the cost of this strategy, because we are buying this many stocks and the stocks are selling at 100. So 100 times 0.4656. But then because we are writing one call option, we will receive the premium, which is equal to C. That's the cost. Now let's go ahead and check what's going to happen if you start with the replicating portfolio a year later, 6 months later, I should say. Well, the stock price will go up to 110, and because you have only this many, so we have 110 times 0.4656 minus, well, the call option will expire in the money at this node, which is 6.984. And if you do this calculation, you get 44.232. And we can do the same calculation at the bottom node. So up, down. So $95 is the price at that node. Times, well, obviously we have 40.4656 shares, minus the call option will go worthless at that down node, and as a result, that thing will come out as, long behold, 44.232, exactly what we wanted. So therefore, now we have this constant outcome from the replicating portfolio, but we could have gotten this much money by simply at the end of the half period, by simply landing at time 0 the discounted amount, right? So therefore we could as well landed 44.232 divided by 1.05 at time 0, and have gotten, if we indeed landed this much amount, have gotten that $44.232. So as a result, by the law of one price, which is a direct consequence of the no arbitrage principle, the cost of these two approaches at time 0 must be equal. So therefore we have 44.232 over 1, let's write that down, 232 over 1.05 is equal to 100 times 0.4656 minus C, but that's just 46.56 minus C, and indeed you can finish the math. From here, C comes out as $4.43. That's it. So we would say that the call option at time 0 is worth $4.43 overall. Now I want to just remind you of a few things. So all we did here is pretty good. So in this 2-period game, we had to solve 3 different 1-period tree structures, but the main idea where we constantly create replicating portfolios using the deltas and then thinking about this replicating portfolio is somewhat challenging, if you will, and it's pretty much the same idea over and over again. So what we can do is we can streamline all this by resorting to some formulations, some formulas, if you will, and the formulas will enable us to solve the problem more mechanically without resorting to the creating a replicating portfolio, which there's obviously nothing wrong with about it. It's a great, amazing idea, but at the same time it is somewhat time consuming, and we can solve these problems in a more expedited way if we can come up with these formulas. And so what I want to do is I want to give you guys time to digest what we learned here and then think about that problem. And in the next video lecture, I would like to actually go over these formulas and how to directly bash these questions. And in particular, I would be interested on, seeing what happens if the stocks were paying dividends. Dividends might be either discrete, periodically, like every quarter or every 6 months, or it might as well be continuous. So I want to continue this discussion of the binomial option pricing model. In the fourth part, like I said, I want to have a look at these shorthand solutions to these problems, and hope to see you guys in our next lecture.